Let us now start looking at a very simple yet insightful domain of mechanism design with transfers, and that domain is the domain of single indivisible object allocation. We have already seen one example, one mechanism which is truthful in this domain, namely the second price auction. But here we will not only try to characterize that which other mechanisms are also truthful in the context of single indivisible object allocation. We will also try to maximize the revenue earned for the auctioneer while selling the single indivisible object. Now the reason is that we get a very rich set of elegant results in this simple setting, and we can actually go beyond the limits of deterministic mechanisms, and we'll look at some randomized mechanisms as well. So in this domain, the setup is the following. So we have the type set for each agents. We will modify the notation slightly so that it is falling in line with the standard definitions of single indivisible object. So the Ti, which is the equivalent of capital theta I, as we have defined elsewhere, this is a subset of real line. So now the type set is a subset of real line, which denotes that if you pick a specific type of an agent I, this denotes the value that this agent gets when she wins the object. So it's as simple as that. And now in this context, the allocation A is a vector of length n that represents the probability of winning this object by the respective agent. This is the first time that we have spoken about the probability of winning an object, or probabilistically deciding certain allocation. So far we have discussed only deterministic allocations, but because of the simplicity of this domain, we can actually give certain results which is also probabilistic in nature, so which is also randomized mechanisms. So this kind of mechanisms where the final outcome or the allocation are probabilistic, those kind of mechanisms we are going to call as randomized mechanisms. We have not discussed this in the context of the previous cases, like the Gilbert-Sutherland setting, or in the context of single picked preferences or task allocation, because it's much harder to get a kind of a characterization result. But because of the simplicity of this domain, we can actually take a look at that, and we'll show that there are certain good results. So therefore the set of allocations in this case is no longer the set A, the set of allocations, the set of pure allocations. Rather it's a probabilistic allocation. So the vector, so this delta of A is nothing but a simplex, where each of these elements in this set is a vector of numbers between 0 and 1, and they all add up to 1. So this is nothing but a probability distribution over these n agents. The object is going to get allocated probabilistically among one of these agents, and in this case we are assuming that the object is definitely going to get allocated. So there is nothing like the object is not allocated. Now what is an allocation rule in this case? As before, the Cartesian product of all the type sets, the allocation function actually maps it to the set of allocations. Now the set of allocation is this simplex over this set A. Alright, so now we have this valuation function which is defined on that kind of an allocation, which could be a randomized allocation and its own type. But now this valuation is just the expected value for that agent, for that object. So AI is the probability with which this agent wins, agent I wins that object, and if it wins, it gets a value of Ti. So this product is giving it the expected valuation. So similarly, when we are talking about f of t, so if we look at the function f and apply, use the type report of all the agents as its argument, then we get a vector whose ith component here is nothing but the probability of winning the object for that agent I. Now let us try to familiarize ourselves with this notation when we are looking at one of the much discussed example of second prize auction, the Vickery auction. So the type here in that case were VIs for all these agents, and let us define when we are looking at agent I, what is the maximum value of all the other agents except agent I. So that is being defined as T minus I of 2. So the 2 stands for the second bid. This 2 will be the second highest bid when I is the highest bidder. Now agent I is going to win if its valuation is larger than the second highest bid. So if this agent has the highest value, so among all the other agents, their maximum value, the agent I's value VI is even larger than that, then that is the maximum among the whole population of bidders. So then this will be considered as the winner, and it will lose if the valuation is less than that. And we can also say we can define a tie-breaking rule when there is an equality. Now the payment. So we know that under second price auction, the winner pays the second highest bid. So if agent I becomes the winner, then it pays T minus I. For all the other cases where the payment where VI is not the highest bidder, its value is going to be 0 anyway. So we can write the utility of this player I in the following way. If VI is less than or equal to T minus I2, it is going to get a utility of 0. If it is larger than T minus I2, the difference is going to be the net utility. So we can plot these quantities, and we can see that the utility has a very interesting shape. Now on the x-axis we have plotted the valuation of this agent, and on the y-axis the utility. Up to this point of T minus I2, the utility of this agent remains 0, and after that it increases proportionally with VI, and because this is just VI, so this the slope of this curve will be 45 degrees. Now the other thing that we can observe, so if we do another plot for the allocation of this agent, we see that up to T minus I2, this allocation is going to be 0, and whenever the valuation is larger than that, then the allocation is going to be exactly equal to 1. So we leave this point of the exact equality open at this moment, because in that case when they are equal, that means that there are at least some other agent who also has the same valuation as this agent. So in that case one can randomly pick any of these agents as winners, and therefore any of these numbers could be a valid allocation for this agent. So we can make a few observations from these two curves. The first thing is that this utility curve is convex. So if you look at this curve, this is a convex curve, and the derivative is 0 if VI is less than or equal to this, and 1 if the valuation is larger than this threshold point, and it is not differentiable at this threshold point. So at this point T minus I2, it is non-differentiable. But whenever this function is differentiable, it actually coincides with the allocation. We can also see that. So these are the two points. In fact, a lot of our understanding of the single object allocation will depend on the properties of convex functions, and therefore in the rest of this module we are going to spend some time to discuss some of these known results from convex analysis. For most of these results we will not provide a proof because they are clearly out of scope of this course. If you are interested in looking at the proofs, you can take a look at some standard text like Rockefeller, but wherever necessary we will provide some sort of a intuition of why this sort of a result is actually true. The first fact from convex analysis is that convex functions are continuous in the interior of its domain. So which means that this kind of a convex function, so whenever you are talking about functions which are convex, you cannot have jumps within a domain of this function. So what can happen is if a function has a, let's say, a domain from here to here, that cannot be, so there can never be any function which has a jump inside this, because then you can actually have some sort of a chord joining these 2 points, which is below the curve at some point. So this is whenever you have jumps, you are certain that that is not going to be a convex function inside its domain. But this property does not hold at the end. So at the last point there could be some jump. So you can have functions which goes all the way till this point, and at the final point there is a certain jump. So that is clearly convex. So for convex functions, it is known that they are going to be continuous in the interior of its domain. So the second fact of convex functions is that they are differentiable almost everywhere. Now, what does this term almost everywhere mean? It means that the points where the function is not differentiable, they form a countable set. So we can see the example before, that exactly at one point, or maybe there are multiple other points where you can actually have it, but you cannot create an interval of points, for instance, where it is non-differentiable. So to be more precise, this set of the set of non-differentiable points of a convex function forms a set of measures 0. So it's something like these points, if you are looking at the whole set, they are almost vanishing. So if you are looking at only finite or countable number of points in an interval which has uncountably many points, those finite or countable points has measures 0. That is how more formally this is said. But let us not worry about those things. It is saying that except for a few points or a countable number of points, the function is going to be differentiable everywhere. Now, I'm sure that this definition of the convex function is known to all of you. So whenever we are defining a function, a convex function, then for every point x and I in its domain, so this is the domain of this convex function, and for any lambda which is living in this interval 0, 1, this is true. So that means that whenever we are looking at a convex combination of any 2 points, so let's say we have a function like this, and this is our x-axis, and we have 2 points, let's say x and y, and we are looking at the corresponding values of this function at these points, so gx and gy, and if we join a chord between them, so therefore lambda times gx plus 1 minus lambda times gy is some point like this, and that point will always be above the value of that function at that point. So this is, let's say this is the point lambda x plus 1 minus lambda of y, and the g value at that point is going to be lying below that chord. So the chord connecting any 2 points will always be above the curve. That is the meaning of a convex function. Now, if that function is differentiable at a point inside this domain, then we denote its derivative by g prime of x. This is quite standard, but we are going to define something which extends this idea of gradient or the derivative, and that is that extension is known as the subgradient of this function. So how is subgradient defined? It is defined formally in this way, but before going into the formal definition, let's look at what is actually what is this saying. So let's look at a very specific point, let's say x, and we are going to a different point y, z in this in its domain, and what we are doing is we are first looking at the value of that function at that point, and then taking the distance. So suppose I have a point like x somewhere, and I'm trying to find out what is the value of this function at a different point, let's say z, and I do a kind of a multiply this with this difference of z minus x with a constant quantity x star, and then add that on top of on top of this g of x. So g of x is nothing but this point here, and then we are taking a slope. So the slope of this this line is nothing but x star, and we are going to this point here. So that quantity, so this point is nothing but g of x plus x star times z minus x, and that point should always be below the actual value of that actual value of the function at that point. If that happens, then we are going to call this x star to be a subgradient of g at that point x. And of course, this I have only shown the positive direction. This should hold for all z, so it should also hold for the other direction also. So in some sense, you are essentially putting a line, finding the slope of the line in such a way that the entire convex curve is lying above it, and that is the point which also touches the gx. So fair enough. So what is the property that it is giving us? So we can actually say that now we have, even though we cannot define a gradient at the point where it is not differentiable. So for instance, the point where this point was not differentiable in our previous example. So in this convex function, but we can definitely define something like a subgradient, and naturally the subgradient need not be unique. So in particular, it is non-unique in those points where it is not differentiable. Like one can have a bunch of subgradients. So similar to, so this is one x star, which is a subgradient because it keeps the entire curve above it. But you can also think of another subgradient which is also keeping the curve above it. So there could be actually many subgradients which are possible. The one observation that we would like to make, the points where it is actually differentiable. So let's say a point like this. So this red colored x, this point, can you actually find multiple subgradients? The answer is no, because if you for instance try to find some subgradient which is not exactly equal to its gradient here, then you might end up having some points which are actually above that the value of that point. So essentially this inequality will get violated if we pick some other kind of a subgradient, some other line. So one empirical observation that we can make here is that whenever there is a point which is differentiable of this, so if the convex function is differentiable at a certain point, then the subgradient actually equals the gradient, and in that case the subgradient is going to be unique. So that is something that we'll state formally. So these are some standard results. So you can refer to that standard text on convex analysis, any standard text on convex analysis. The first result is that, so suppose we have a convex function g, and x is in the interior of I, and g is differentiable at x. Then g prime x is the unique subgradient of g. So we have already told the intuition. So this is the formal statement, and it is not very difficult to show even formally. All that you need to do is to reuse this this inequality for the points which are above x. So let's say x plus epsilon, and also points below x minus epsilon prime, let's say, and then use the definition, the fundamental definition of derivatives, and one can show that this x star will be sandwiched between the left derivative and the right derivative, and the points where it is actually differentiable, this left and right derivatives are same, so therefore this x star must be equal to that derivative. So that is the proof of this lemma. So for lemma 2, again we have a convex function, and one can say that this function always has a subgradient at all points in I, so including the h points. So the earlier result was only for interior points, but this result is true. The subgradient exists for all points in I. The next fact that we'll be using it says that if you collect together all the points where g is differentiable and denote it with I prime, then the points where it is non-differentiable, that has that is a set of measures 0. And in addition, the set of subgradients at a point forms a convex set. So let's say we look at a bunch of points. So there will be some points where the function is differentiable. We have already seen that those points essentially, so those kind of points are almost everywhere. So the function is differentiable almost everywhere. And in those points, the derivative exactly is equal to the subgradient. The points where it is not differentiable, which is a set of measures 0, in those points the subgradient might be many, but they actually form a convex set. So it is something like an interval within which all the subgradients live. So you can think of the previous example here. So the subgradients will start from this point, so which is a negative gradient, to this point, which is a positive gradient. So all these points, so you can think of this as the left derivative at this point green x, and this slope is nothing but the right gradient, and all the points between this left gradient to right gradient in that interval, all those points are subgradients of this function at that point. So that is exactly what is we are going to state as fact 4. So if you look at the right gradient and the left gradient of this function g at that point, then the set of subgradients at x which are non-differentiable lives within this interval from g minus prime x to g plus prime x. So we'll use a shorthand notation to denote the set of all subgradients at g of g at a certain point by this del g of x. Lemma 1, by lemma 1 we already know that the points where it is differentiable, so these are the set, this is the set where the function is differentiable, it is a singleton. For all the other points it is non-empty. So the next lemma that will be very much useful for us is that of some sort of a monotonicity. So we know that if it was a convex function and it was differentiable everywhere, then we know that the derivative is monotonically increasing, right? I mean, this is coming from the fundamental property of convex function. We can extend that idea to subgradients, and we can also say that the subgradients, when you are defining a function so there are points which are where it is differentiable, there you know that the subgradient is unique. For the points where it is non-differentiable, you just arbitrarily pick one of those subgradients and define a function in that way. So that is how we are going to define this function phi. So phi of z is an element of this delta gz as we have defined for the points. So for all the points in I, so for all the points in I prime, we already know that this set is going to be singleton. For all the points I minus I prime, where it is non-differentiable, we just pick one point from that set and define the function in that way. Even in that situation, we know, so this lemma is saying that if you have have x greater than y, then the corresponding function phi will also be non-decreasing. So it's a monotonicity condition on those subgradient function. And you can actually visualize this. So here, all these points on the left hand side, they were having the subgradient to be negative. So let's say call this minus of 1, and suppose this gradient is plus 1. So as we move from this direction to this direction, we see that the subgradient, this phi function, starts with minus 1. Let's say it starts, so this is the phi function, and it starts with minus 1 initially, and at this point you can arbitrarily pick any point, so it might be any number between minus 1 and 1, and then you have this the rest of the points, so this changeover happens at this point, this x. And then onwards you can see that this function increases. The function is always non-decreasing. That is the conclusion from a convex function. And the last result that we are going to state here is an integral formula involving the subgradients. So we can actually find for any pair of points x and y that is living in this domain of this convex function through this integral formula. So we can find the value of this convex function at point x starting from point y, looking at the value of the function at point y, and then integrating from that point to this new point from y to x using this this subgradient. So what it is actually saying, this is something like similar to the derivative formula. So what is subgradient? It is the gradient except for a few points where it is not differentiable. But we already know that those points are kind of countable and has measure 0. So this integral will just chop off. So of course this requires this needs to be proved rigorously, but the point is that those points are just one point. They have measure 0, so we cannot really integrate. The integral over those points will be 0, and for the rest of the points we are just looking at the derivatives. And therefore when we want to find this function g of x starting from g of y, we can just use this integral formula and get the value. So that this particular lemma will be very much useful when we try to characterize the payment of the single object auction mechanism in our next modules.